Well, welcome back, ladies and gentlemen. I hope you're really dialed in and ready to rock and roll tonight because the area between two polar curves can arguably be maybe the toughest, most challenging topic of the year. I mean, it ranks right up there with some of the best. And it's really, I think conceptually it's not too bad. It's just a different way of thinking. You know, this whole unit with polars is like learning a different language. And that's what poses the biggest challenge. So conceptually, I don't think it's bad, but just in terms of the way we're going to set up our integrals and recognizing when to use more than one integral and stuff, that's a little bit challenging. But as far as we want to find the area between the red polar curve and the blue polar curve within the finite bounds of alpha to beta here, and generically, here's how we're going to set this rascal up. The first integral I'm going to set up. We're going to integrate from alpha to beta, and I'm going to do just the red curve. And in fact, I'm going to write red just because that's the easiest thing to do, I think. So this integral right here represents, wow, why is my pen's really dying here? Okay, that integral alone represents everything inside that red curve from the pole all the way to the red curve. So we've got these wiper blades rotating counterclockwise, and they're gobbling up chunks of area all the way across. Now, I'm going to write another integral here in blue, and I'm going to say 1/2 integral from alpha to beta, and then I'm going to say the blue curve, okay, which would be the inside one, squared. So that integral is measuring everything inside that blue curve, everything inside of here. And quite simply, I think you can predict the next step. What we want to do is we want to subtract these two integrals. And when I subtract them, all I'm going to be left with is that what was originally green space in here. And quite frankly, we're now going to condense those two integrals into one really nice clean integral. Whoops. Got some stray marks here. All right, so we're going to say 1/2. And the only reason we can combine these two integrals into one integral is because they do have the same bounds. And we're going to say the outer curve, which used to be our red one, squared, minus the inner curve. In other words, outer means whichever one's further from the pole, inner means whichever one's closer to the pole. And this is how we're going to find the area between two polar curves. Well, we're going to jump right into our biggest challenge today, and we're going to ask this big question. Every time you get your drawing drawn and you start shading in the area they want you to find, you ask yourself, can I do it with just one integral, or do I need two or more integrals to find the total enclosed area? Back when we did rectangular coordinates, we used to say, well, whenever the upper curve changes, we would stop and set up a new integral. Well, now, here's the deal. I want you to get in the habit of drawing a radial line each and every single time you see an intersection point. This is a very important habit to get into, and it's going to help us a lot. Draw a radial line each and every time you see an intersection point. So what I've done is I've brought up what I consider to be one of the more challenging examples that I've ever seen on an AP question. Let's call this R sub 1. We'll call this circle over here R sub 2. We're not going to worry about the particular equations. This intersection point right here, I'm going to call that alpha sub 1. This intersection down here we'll call beta sub 1. I guess the subscript's not real important on those guys. I'm going to go over multiple different ways to set up the area between these two curves. Notice the area between these two curves is a combination of both the blue and the red regions. We'll talk about several different ways, and then we'll talk about what we think is the most efficient integral. The first one here that I want you to think about is, okay, here's 0 radians, right? What we're going to do is we're going to start to rotate up. Rotate up, rotate up, rotate up until you hit alpha. Okay, so what I'm thinking is from 0 to alpha, okay, I integrated everything inside of R sub 2. All right, notice I do not need to include or acknowledge that R sub 1 even exists within those bounds. Now, on top of that, I'm going to now try to find the area of that red sliver. And what I'm going to do is this one is going to start at alpha, and it's going to go until I hit pi over 2. Okay, what happens is let's see, I wish we could zoom in a little bit on this rascal. But what happens is we have very thin radial lines in here, and they're rotating up, they're rotating counterclockwise. And once you hit pi over 2, the radial line has a length of 0 because that's when the curve r sub 1 comes back and hits the pole. So let's see, I would now say r sub 1 quantity squared d theta. And within those bounds from alpha 1 to pi over 2, we don't even need to acknowledge that r sub 2 exists. All right, now that's the sum of those two integrals is giving me everything up here. And all I'm going to do is I can now wrap that rascal up and now double it to give me all the total combined area both above and below the x-axis. And of course, doubling it's going to kill those coefficients. If you were overwhelmed at all in that last example, I don't want you to panic at all. We get a few examples under our belt here throughout the rest of the video. We'll come into class tomorrow, we'll practice some more. This is definitely a topic that's going to take time, but by the time we're done, we will be very good at them. So here's our first example today. I want you to find the area that's bounded inside of r equals 1 plus 2 cosine. So that's the limicon with the inner loop. And yet outside of the equation r equals 2. All right, so we want everything inside of 1 plus 2 cosine and everything outside of r equals 2. And what I've done is I've represented that area that they're referring to by shading it in an orange color. So we're going to try to go find that orange crescent moon-shaped object. And the first thing we want to do, and we're trying to ask ourselves this question: can I find the area of that orange crescent with one integral, or do I have to use more than one integral? And so what I did is I recommended that we always get in the habit of drawing a radial line every time you see an intersection. And these two curves intersected right there, and so I instantly drew this radial line. All right, and I want to figure out what degree or radian corresponds to that radial line. Now there is a second one down here, but again, like most of these polar curves, we're probably going to take advantage of the symmetry. We're going to find the area of the top half of that crescent and then double it eventually. So here's the trick. How do I find that intersection point right there? All we're going to do is we're going to set those two equations equal to each other. We're going to say that 1 plus 2 cosine of theta is equal to 2. All right, we'll subtract the 1 over. We'll divide by 2. And when does cosine equal 1/2? Once in the first quadrant at pi over 3, and then once in the fourth quadrant at 5 pi over 3. All right, so that first intersection is pi over 3, and this one down here is 5 pi over 3. See if we can squeeze that in here. Okay, so those are the two intersections. Now what I'm going to do is I'm going to start here at 0 radians, and then what I'm going to do is I'm going to rotate counterclockwise and just gobble up chunks of area as that wiper blade sweeps in a counterclockwise motion. So I'm going to set up an integral to represent just the part that I've shaded in so far. All right, what would that look like? So I'm going to say 1/2 integral from 0 radians up to pi over 3 radians. Now I want to start with the outer curve, which is 1 plus 2 cosine of theta squared minus, whoops, almost forgot squared, the inner curve squared. It's kind of like upper minus lower, except now it's outer minus inner. And that integral right there represents that top half. Now, if I wanted to now add on top of that, switch colors here. Let's say I wanted to now, we're going to rotate around, and we're going to start right here at 5 pi over 3, and I think the direction that you move in is important. Notice I'm continuing to rotate counterclockwise. What integral would represent that blue region? Well, let's say 1/2 integral from 5 pi over 3 all the way until you hit 2 pi. And then again, it's still going to be the outer curve squared minus the inner curve squared. Okay? Now, obviously, we could maybe be a little more efficient and combine these two integrals into one integral. And in fact, all I'm going to do is you could take either one of these and simply double it. And that's what I'm going to recommend that you get in the habit of doing. So I'm going to take that red one right here. I'm going to steal that one. And if I double it, so I'm going to say 0 to pi over 3, 1 plus 2 cosine squared minus 2 cosines, or just 2 squared. Oh my goodness. So there it is. That one integral would give you the total combined area of that crescent-shaped moon. Our second example is still fairly friendly. We're going to find the area enclosed between r equals 1 plus cosine of theta, and then r equals just regular cosine of theta. Now I think it's important to have expectations about what these polar graphs are going to look like before you start anything. That first one, 1 plus cosine, is going to be a cardioid. Again, if it helps to draw the rectangular graph first, I want you to go ahead and do so. The second one's just going to be a plane circle that's symmetric with respect to the old x-axis. Now with cardioids, it takes 2 pi radians to complete one cycle, but with those circles, it just takes pi radians to complete one cycle. So that's a good reminder right there. So let's see if we can attempt to draw these. The cardioid is going to start at 2 here. It's going to hit 1, it's going to hit the pole, it's going to hit 1, and then right back. So we've got that nice sharp non-differentiable point at the pole, looks like that. And then we'll switch colors here. In the circle, r equals cosine. Because the coefficient is 1, it simply has a diameter of 1. It's going to start right here, and it's going to rotate that way. So again, we want to find the area that's in between them. So what I'm going to do is I want to find the area that's in here. We'll just picture those rays of sunshine, or those radial lines sweeping in that direction. And what I'm going to do is I'm going to set up an integral to find the part I have shaded in right now, and then we're simply going to double it to get the whole thing, and just again taking advantage of that symmetry. So here's what I'm thinking. The biggest trick with this one is that we definitely need 2 integrals for this one, because of the fact that it it takes fewer radians to draw out that circle. So I'm going to start with the cardioid. The cardioid, what I'm going to do is I'm going to go from 0 to pi. All right, that's going to take me from here's 0 and all the way around the horn. Right there, that's where pi stops. So I'm going to integrate from 0 to pi, and I'm taking 1 plus cosine of theta. I'm going to wrap it up, square it, d theta. All right, minus what? Now keep in mind, if I'd used the same bounds and went from 0 to pi, I would actually find the area of everything in the circle. I only want to do the top half of the circle right here, okay? I only want to do the top half. So I'm going to say the integral from 0 to pi over 2 cosine of theta squared. All right? And so this first one represents everything inside of the cardioid. All right. The second integral represents everything inside of the top half of that semicircle, and we subtract them, and that would give me the total area bounded between the two of them. Now, actually, not quite the total. Let's do this. Let's wrap this up after we subtract them, and of course, we're now going to double it to give us all of this area in here as well. All right, last one for today. We're going to find the area of the region bounded by r equals 1 plus cosine of theta. So there's another cardioid, just like we saw in the last example. Same everything. And then the second function is going to be r equals 3 cosine of theta. All right, so a little bigger circle this time. So really, the only thing that's new is we threw the 3 in there. So we're going to try to draw this the best we can. And let's see. I'm going to need enough room here. Let's see. Let's go 1, 2, and 3. The cardioid's going to start right here. Hit 1, hit there, hit 1. All right. So I should be getting better at drawing these cardioids, you'd think. All right. Not too bad. All right. Now, we're going to have to pay special. This is going to be have a circle with a diameter of 3. So we're going to start right here. And it's going to swoop up and around. Alright, maybe I could bend that out a little bit more. Okay, let's see if that erases just a little bit. Yeah, I really want this to be curved right there. Okay, so we've got to find the area where those two graphs overlap. And basically what we're going to... the most important thing we need to do here is to find that intersection point right there and draw a radial line straight there. And what you're going to find out is we need two separate integrals. All right? And you're thinking, why do I need two separate integrals? Well, the first thing we're going to do, we're going to start at 0 radians and we're going to rotate counterclockwise, right? Well, everything up till you hit that red line is bounded by the brown graph, or the cardioid. Now, once you hit that red line, things change, and you're now bounded by the blue graph. So there's that little sliver there of green radial lines that needs a new integral. So we're going to do an integral for orange, then we're going to do an integral for green, and add them two together, and then at the very, very end we'll wrap it up and double the whole thing to account for the bottom half of this graph. So let's start with the red guy. Let's see, I said red, what the heck. Let's start with the orange shaded region, which is going to be, let's say, 1/2 the integral from 0 to something, and then 1 plus cosine of theta squared. And like I said, probably every student in the country is going to have this much on their paper. All right, the question becomes, can you figure out that upper bound? Quite nicely, it's just a matter of setting those two equations equal to each other. So I'm going to say that 1 plus cosine of theta has got to equal 3 cosine of theta. Let's see, let's subtract a cosine of theta over. We got 1/2 equals cosine. So again, you should expect very nice bounds. The first bound is going to be pi over 3. Then the one down here would be 5 pi over 3. But pi over 3 is really the one we want. So pi over 3 is going to be the upper bound. Now, on top of that, we need to go try to find the area of the green guy. So we're going to say 1/2 integral from pi over 3, and then when you hit pi, that's when, or I'm sorry, pi over 2 is when that blue graph gets back to the pole. And now the blue graph is just 3 cosine of theta, wrap it up and square it, d theta. And the sum of those two integrals is going to give you the total area combined by those two graphs, with the exception of now we've got to wrap it up and double the whole thing, and that'll account for this area down here as well, and now you really do have the total area. So there's a couple of really good examples. Don't be afraid to rewind and rewatch this one a few times and really be able to visualize the need for two integrals and visualize the bounds, when they start, when they stop, and all that good stuff. So good luck. We'll see you tomorrow.